Okay, so we're going to talk about different transceiver controls to start with here. And I know I ask this question all the time. Can you see this list of participants on
We
the
have
screen?
our own view of it, but we don't see the one on your screen.
Okay, good. Because I'll just leave that up in case anybody else wants to join. And I'm using the favorite IC7300 because I already had the image. And so we're going to talk about all these different little controls of a typical HF transceiver. So you got the attenuator, the notch filter, the S meter, and because as I was going through this, I realized I had some things sort of not in the most optimal order to teach a class, so I've reordered it a little bit. There was this section, the starting section, then it jumped to test equipment, then it jumped back to S meters and speech processors. Well, I moved the S meter and speech processor section up. So we're going to talk about that in order. So one of the greatest things about these new modern amateur radio transceivers is all the filtering that's available, and it's all done in software, right? I mean, like this radio here is little. It's like this big, and it has like probably 3 or 4 different processors in it. One of them is a digital signal processor, and it's doing like all the it's doing this notch filtering. It's doing speech processing. It's doing these 2 functions: noise reducer and noise blanker, and it's doing it all in software. It's just amazing, and that's why we can get such a fancy display here too, because everything's being done in the computer, and so this is just another computer display here. I compare this to the radio I had before this. Before this, I had an ICOM IC746 Pro, and that radio was about 15 years old, and it had digital signal processing in it too. But the digital signal processing in this radio is just so much better than that. Like when I got that radio, I thought, oh man, this is a great radio, the 746 Pro. And I, even when these came out, I said, well, like, why would I want to upgrade it? Because, I mean, the 746 Pro is just so good. Well, I got a good deal on one of these, and so I bought it, and it's like, oh man, this 7300 is much better than the 746 Pro. And I think, and so what's happening here is you don't want to just necessarily buy a radio at DSP, but if you buy the latest radios, like the 7300, you get the advantage of faster processors and probably better software algorithms. So it can do all this signal processing in faster and better than the older radios that had digital signal processing. So it's quite something, actually. It's really quite something. So having said all that, let's talk about some of these features. So the first thing we'll talk about is the notch filter right here. And the control for the notch filter is right here. So when I press that button, I get a notch filter. So the question is, what is a notch filter? So let's look at that real quick. So you have a bandpass filter, and in this case, if this was for a single sideband signal, this bandwidth here would be 3 kilohertz. And well, so if you had a signal sort of come on frequency that was, say, like right here, like say somebody came on with a carrier right here, you would hear that carrier in your earphones or whatever. Well, if you turned on the notch filter, if you can think of, and I wish I could do this, and I tried, but I couldn't get it to work. If I could sort of superimpose this notch over this bandpass filter right over the carrier, I'd have something like this, and that carrier, I would make that carrier disappear. And these things work amazingly well. And in fact, on single sideband, it's automatic. It somehow the software sees this tone, because that's how it appears, as a single tone, and then we'll move that notch right over that tone, that constant tone. So, I mean, it is like, it just makes that signal just disappear like magic. On CW, usually you have to, because everything's a tone, right? On CW. So if this was a bandpass on CW, and so let's say it was, 500 hertz for CW, and this signal came on, you actually have to adjust it. You have to tell it what the null frequency you want. If it's like 200 hertz away, you want to set that for 200 hertz or something. 200 hertz. So on CW it works a little different, but it's the same. It works just as well. So question: what is the purpose of the notch filter found on many HF transceivers? Answer: to reduce interference from carriers in the receiver passband. So that's what this is, the receiver passband. Another thing you could do, which some radios have, is what's called IF shift. So if you're tuned to this frequency, and again, I can't really do this, but if you could imagine shifting that passband over, say in the CW case, say 200 hertz, what you then would see is that the passband would look something like this. And again, you've filtered out that offending carrier here because you've shifted the passband left or right in this case. But whatever. If the carrier was over here, you'd shift it the other way. So that's called IF shift. And all these radios can do all this now. It can do either one. I kind of like the notch filter over the IF shift, because what can happen if you had a carrier out here that you weren't hearing because it was outside this passband, when you shifted, then all of a sudden you would be hearing it. So it's kind of better to use the notch filter, or simply narrow the filter period. So if you, like in this case, if the signal is here, if you made just the filter narrower, say to like 100 hertz now, or it's probably more like 200 hertz, then you wouldn't hear that signal either. So with these new radios, you have all this filtering capability, and they work excellently. I mean, in the IC746 Pro, it had a notch filter, and it worked pretty well, but it just works much better with the 7300. And again, I think it's because there's more processing power, and the algorithms are better. All right, any questions about notch filters? They're just so cool. So let's go back to this now. Oh, not that one, this one. Another control we have is the attenuator. And where's the attenuator on here? It's right here. So when you press this button, you set either the amount of amplification you want from the preamplifier, or you switch in the attenuator, and you see it on the screen here. I know it's kind of small. I'm sorry about that. But why would you want to use an attenuator? Well, sometimes signals are so strong that that you want to attenuate them, because they'll overload your radio and bad things can happen. As far as hearing it, not damaging your radio. The signals never get quite that strong. Question, what is one reason to use the attenuator function that is present on many HF transceivers? Answer, to reduce signal overload due to strong incoming signals. And so it just prevents overloading your radio. And you know, these radios are so sensitive. You know, I've talked about this Flex 6400 radio I have. I you know, everything's on the screen in this Flex, and I couldn't. In the layout is a lot different than the radio like this. Here, at least you have a real front panel and you got some buttons. And even though it's only controlling the way the software, you still got button knobs to control, you know, set the controls. And so anyway, we were talking about this at lunch, and me and some ham friends. And I said to him, I said, you know, I don't even know where those controls are on the Flex. And they all got a laugh out of that. So when I got home, or the next time I sat down in front of the radio, I looked for it. And I found it. I found where the controls were, but it had already been set to attenuation. So this radio, which I thought was even more sensitive than the 7300, was more sensitive even with the attenuator on. So it's kind of amazing, but that's the way it works. I've never turned on the preamp at all on this Flex. It's just been so sensitive. So anyway, sometimes you might want to use the attenuator. Noise blanker and noise reducer. Now these things do the same thing, but on different types of signals. Okay. So question, how does a noise, oh, and here's where these are, right here. Question, how does a noise blanker work? Answer, by reducing receiver gain during a noise pulse. So if you have pulsing noise, you want to use the noise blanker. If you have like more random noise, like lightning crashes and just general atmospheric noise, that's when you want to use the noise reducer. Question, what happens as the noise reduction control level in a receiver is increased? Answer, received signals may become distorted. Well, that's what happens, right? Because what you're doing is you're clipping the noise, you know. So if you had, you know, like random noise, you turn on the noise reducer and basically it clips these higher level peaks here, and that distorts the signal. But again, on the newer radios, it doesn't do it. Doesn't seem to distort it as much. On the Flex radio I have, I can turn on the noise reducer and I don't hear that kind of distortion. Whereas on the IC746 Pro, you could tell it was definitely distorted. Again, it all has to do with I think the faster processors and better algorithms. So these two, you know, and honestly, this noise blanker function, it really doesn't work that well. Like even on the 7300, it doesn't work that well, and on the Flex, it really doesn't work that well. The noise reducer, though, does work pretty well. It works pretty well both on this one and on my Flex. So I don't know. Just take that for what it is. All right. Electronic keyer. And I wrote it up here because really the keying, the setup is all in the menu function. And at least on this radio, the plug for the key is in the back of the radio. So you have to look in the back. But what an electronic keyer does is generate automatic dits and das, right? If you're sending Morse code, you have what's called a paddle. Paddle has two switch closures. One switch sends an automatic series of dits. The other one sends an automatic series of das. And by moving it back and forth, you send the characters of the Morse code. It used to be that this was not a part of any radio. I mean, this was like a separate accessory, but now they're all built in. It allows you to set the speed at which you're sending, and sometimes has memory so you can, pre-can certain messages like sending CQ, and yeah, it works great. So question, what is the purpose of an electronic keyer? Answer, automatic generation of strings of dots and dashes for CW operation. Another function is this reverse function. So question, what is one advantage of selecting the opposite or reverse sideband when receiving CW signals on a typical HF transceiver? Answer, it may be possible to reduce or eliminate interference from other signals. So here's the idea. Usually you set it up to receive sort of like one sideband or the other. And if the interfering signal is here and you're using the lower sideband setup, if you go to the reverse, then you're going to use the upper sideband, and you won't hear that signal. That signal won't be there. Yeah, I kind of don't like this feature. I always leave mine set to lower sideband no matter what, especially because with all the other fancy filtering, it's pretty easy to get rid of that. And using the lower sideband is more the standard than using the reverse sideband. Any questions? All right, let's talk about split. Oh, I didn't put that on here. So split. So on this radio, when you push this button, you're now operating in split mode. What does that mean? That means you can set the transmit and the receive frequencies to be different. So why would you want to use this? Well, if you're trying to contact the DX station, there's a good chance you're not the only one trying to do that. So if the DX station is on this frequency and 10 stations or more are trying to contact them, trying to do that all on the same frequency would be pretty tough. So in this case, the DX station will usually specify that the operator is working split, which means he or she is listening either up the band or down the band from the frequency that they're transmitting on. Usually it's up. So all the different stations are gonna transmit, up in this frequency, and the DX station is going to be transmitting on this frequency. That allows everybody to hear the DX station, and allows the DX station to choose which of the stations calling him or her that he wants to reply to. So we call that split. Question, what is normally meant by operating the transceiver in split mode? Answer, the transceiver is set to different transmit and receive frequencies. Now, there's two ways to do this. One is with a single VFO, variable frequency oscillator, or with two variable frequency oscillators. In this radio here happens to have just a single VFO. So when it's receiving, it's going to be receiving on this frequency, but when you start transmitting, it'll start transmitting on a split frequency, on a frequency up 1 or 2 or 3 kilohertz from, in the CW anyway, from the DX station. If the receiver had two VFOs, though, you could set one VFO to this frequency, another one to this frequency. And you could be, you still get the same kind of operation, but you're using two VFOs to do it. What does that let you do? Well, it lets you, in the single VFO, you can only listen on one frequency. With two VFOs, you can listen to both frequencies simultaneously. And that has some advantages. So a question, which of the following is a common use for the dual VFO feature on a transceiver? Answer, to permit monitoring two different frequencies. So in this case, you'd be monitoring the DX frequency and the frequency you were transmitting on. You could also set it up to operate to monitor two different bands, even if you wanted to, or you could monitor a CW frequency and a phone frequency, that kind of thing. My Flex, it does have two VFOs in it, so I can simultaneously monitor two different frequencies. So some of them, like I have the Flex 6400, the Flex 6600. You can monitor four different frequencies, so it's got four VFOs in it. It's kind of a to me that's kind of overkill. I rarely even use two VFOs, but maybe some guys are better the operators than I am, I guess. All right, any questions about that?
What are you doing up there?
Yes, Dan. Is it expected that if you're responding to someone that's on the DX and you respond on a different frequency, are you expecting them to just find you, or do you have to tell them where to?
No. What they'll do is they'll say up one or up two or just up, and if they just say up, what you do is you look for all the signals on this waterfall, right? And you can see, because as soon as they stop transmitting, you'll get a big rash of, let's say this is where the signals are. You'll get a ton of signals in this area, right? So you can see how wide that pile, they call it a pileup. You can see how wide the pileup is, and then try and choose a frequency. And so it's always up to the DX station to make the call. So you just throw your call sign in there and hope they hear you. It's kind of stupid, but that's the way it works. But so like here, well, this is probably a little too wide, but because this looks like about 20 kilohertz here. Well, it wouldn't be that wide. It would be more like maybe 5 or 10 kilohertz maximum. But one of the cool things about this pan adapter, though, then, is you can set it to be really wide. So, say this is 5 kilohertz away from the DX station, and you see all these signals in here, right? Well, you can use this pan adapter to find an empty spot. And I've done this, and this works great. So you set the pan adapter as wide as possible. You see where the empty spots is, then you can start transmitting on this frequency. You wouldn't want to transmit on the frequencies where stations are already transmitting, because then they'll never hear you. They'll hear 2 or 3 stations on that same frequency, and they won't be able to pick you out. So you want to choose the empty spots. I'm not a big DXer. I don't really have a really great antenna, but every once in a while I'll get in these pileups, and every once in a while I'll work a cool DX station. I'm more of a casual DXer. Or I don't know if you remember the movie The Accidental Tourist. I'm sort of an accidental DXer. Any other questions?
Thank you.
All right, so for some modes we operate, and we talked about this before, we operate audio frequency shift keying, like RTTY. You can run an audio frequency shift key. So it relies on the audio signal coming into the radio to shift the frequency up and back. to do this properly, you need to set the microphone gain properly, right? And that's actually all of these features are are set by the multi control, and you basically push the button on this radio. It's a push button, and you, as well as a knob, you push it to select what function you want to control, and then you turn the control back and forth to set whatever the parameter is. One of them is mic gain, and mic gain is very important for the for operation of audio frequency shift keying, because it's really you're sending an audio signal. So you want to make sure that is set properly. If not, then the ALC, the automatic limit control, will start activating, and the signal could become distorted. And in sometimes in sideband, that's not a big deal because it's a voice signal. But if you're trying to send an audio frequency shift keyed signal, then it could be, because you don't want to send a distorted signal, because you're just trying to actually send a carrier, just shift the carrier. So question, what is likely to happen if a transceiver's ALC system is not set properly when transmitting AFSK signals with the radio using single sideband mode? Answer, improper action of ALC distorts the signal and can cause spurious emissions. So, that just like when you're transmitting a regular sideband signal, you still want to adjust it properly, and because not setting it properly can cause distorted signals, and those distorted signals lead to spurious emissions. Any questions about that? Okay, another thing that can cause problems is you can pick up RF on the audio cable. So how do you send AFSK signals, right? So you got a PC, and you can connect into the microphone, or you can connect into the auxiliary jack in the back, and you're connecting. If you remember, you're connecting your sound card in the radio, or an external sound card, to the audio input and audio output of the radio. Well, these audio cables can pick up RF, right? And when that happens, you can get distorted signals. So question, which of the following could be a symptom of transmitted RF being picked up by an audio cable carrying AFSK data signals between a computer and a transceiver? Answer, all of these choices are correct. The Vox circuit does not unkey the transmitter. So in this cable, you're also keying the transmitter. It's like the push to talk. In this case, you're using Vox, right? But it's push to talk. It's keying the transmitter. So if you get RF, it's possible that the transmitter won't unkey when you want it to. The transmitter signal is distorted. Frequent connection timeouts. So that all those can happen. That frequent connection timeouts really happens more so when you're using a USB cable. And this radio has a USB connection. So you don't even need the audio cables. You can just connect by USB, and it'll send the audio back and forth digitally. But that's where you get the timeouts and that happened to me. When I first got this radio, I said, oh, this is cool. I'll just hook up the USB cable and get rid of this audio interface I had. And as soon as I keyed up the transmitter, just weird things happen. Well, what it was I was using a cheap USB cable, right? And if you're connecting, well, like this microphone here, I got this connected to the computer with a USB cable. Well, in this case, that probably worked fine. But when I'm transmitting 100 watts of power from an antenna, that's not too far away, and the cable can pick it up. So what I had to do is, unfortunately, I had this in my my chest here, I had to get a really well shielded cable, shielded USB cable. And as soon as I connected that, everything started working fine. Well, that's because the shield was protecting the data signals from the transmitted RF.
Come here, Faith. Faith. Come
Yep. And was there a question?
here. Yeah, she's my girl.
Okay. So any questions about that? All right. I'm going to skip these questions on the amplifier for just now. We'll pick up on this later. Right after this, I should have changed that. So now let's talk about the speech processor. Again, I know, like I said, the speech processor is controlled by that multi-control. And what you're controlling is the level of speech compression. So the question is, what is speech compression? So when you're talking on sideband, the audio signal looks something like this. This is with no compressor. And if you recall, the power you're outputting is proportional to the volume of your audio, right? So the louder you talk, the more power you're actually putting out, the more average power. So what the speech compressor tries to do, what the speech compressor tries to do is to increase the average power by amplifying when the signal's not so high in amplitude, and sort of reducing the power, reducing the amplification when you do have a good signal. So like here in this case, right here at this point, there's no amplification because the input signal has a pretty high amplitude. But here where the signal is where the signal is pretty low, it does amplify it. That increases the average output power of your single sideband transmission. So what you're intentionally doing here is intentionally distorting the signal. You're intentionally distorting the output signal or the audio signal to give you increased output power. And in shortwave radio and HF radio, the goal is not usually high fidelity, but getting the signal through is intelligibility. And that's what the speech processor does for you. Now you can go overboard and crank it up too far, and then it really becomes unintelligible. But there's a sweet spot in there, right? There's a sweet spot about, maybe 10 or 20%, 30% compression, depending on your voice characteristics. I tend to talk kind of loudly, so I would set it a little bit lower. Somebody who's not quite so loud voiced would set it maybe a little bit higher. But the whole idea is to get more average power out so that you're more intelligible to the receiving stations. Question: what is the purpose of a speech processor as used in a modern transceiver? Answer: increase the intelligibility of transmitted phone signals during poor conditions. Well, it's any conditions, really. Question: which of the following describes how a speech processor affects a transmitted single sideband phone signal? Answer: it increases average power. So these usually work pretty well. Question: which of the following can be the result of an incorrectly adjusted speech processor? Answer: distorted speech, splatter, which is signal distortion, and excessive background pickup. So because it's amplifying weak signals or lower amplitude signals, and if you got some background noise, that's going to generally be lower amplitude than your voice. It'll increase the increase the sound of the background noise as well. But these work really great. You know, I'm not a big phone operator, but when I get on, I always run the speech compressor a little bit, and it does really help. It does really help. Just don't crank it up too high.
Are the parameters on the compression controllable, or is it just an on or off feature?
Yeah, that's what I was saying. So let's. In fact, we're going to go back here anyway. Whoops. You know, this knob, you know, you select that function, and it'll give you a level. So you crank it up to a certain level, and you know, and usually I don't know. Let's see, how's it usually gradated? Sometimes it's in percent, sometimes it's in dB, I think, but yeah, it's continuously adjustable. That's why I say for somebody with a softer voice, you want to crank that up a little bit more. For myself, I tend to crank it down a little bit, because again, you don't want to. And you know, the guys will not be hesitant to tell you. You know, if you get on and you got your compressor set like too high, they'll say, "Hey, turn that compressor down a little bit." Even though HF radio is not really high fidelity radio, there's for some reason lots of guys seem like obsessed with audio quality. I've never quite understood that, because to my ears, I'm not really a good one to judge audio quality. I mean, if I can make out the words, that's all I care about. But some people get really excited about audio quality. That's why I'm glad. I must have a good voice for phone though, because I always get told I have good audio, and so maybe it's just my voice. I don't know. But I find that kind of funny, because I really don't operate that much phone. I'm more a Morse code operator. Any other questions?
I got a quick one.
Yeah.
Do some of these radios have some sort of monitored circuit or something? How do you know?
Good question. They actually do. So let's see. Where is that here?
A way to hear yourself without transmitting.
Yeah, there is. You know what? I don't see a button on this radio.
See, there's input for phone.
Is it the green on the lower right?
Green button on the right? No, on the IC746 Pro, there's a button that says MONI. And so you hit that, and you'll be able to hear yourself as you talk. Here, maybe you got to, where is it? Maybe you got to set it up somehow with the menu. But yeah, there is a monitor. It's called the monitor function usually, and you can hear yourself talk.
Cool.
And of course, that only works pretty well if you listen if you have earphones. But yeah, you can do it. Yeah, that's the other thing about these radios. There's so many features, and there's so many different ways to get at them that it's hard. Like I kind of like the ICOMs because I'm used to ICOMs, and even though the 7300 is there's more menus and stuff on the 7300 than the 746 Pro. The buttons are all labeled the same, and that are on here, and they all do this similar function. So this was easy to learn, but if I tried to go to a Kenwood or a Yaesu, I might have a little bit tougher time. That like there's one of the radios I sometimes use on field day is a TS590, and it's just different, and so I got to learn how to use that radio all over again every year. But yeah, good question. Any other questions? I never tried that actually. I should try that. I should like turn on the monitor function and crank up the speech processor as high as it can go, just to, hear myself talk, here to see, see how it sounds. The other thing here, talking about all this, on this radio, you can see the audio. So that's what this is actually. You can tell it to display the transmitted audio. And so you can actually see if you're clipping or not. And you can, as you crank that compressor up, you could see how the signal changes. I've never tried that, but you could do that. So that's another interesting feature. All right, S meters. Let's talk about S meters. The S meter on this radio is right here. And what it provides is a relative signal strength indication. All the radios have them nowadays. Question, where is an S meter found? In a receiver. What does an S meter measure? Received signal strength. Question, how must the power output of a transmitter be raised to change the S meter reading on a distant receiver from S8 to S9? Answer, approximately 4 times. Well, why is that? It's because S meters are supposed to be, and I say supposed to be because they're not all, supposed to be one S unit is equal to 6 dB. If you recall, 6 dB is a ratio of 4:1. So if you were transmitting with 100 watts, say, and you were S9 at a location, if you reduced your power to 25 watts, you'd still be S8 there. This is how QRP actually works. So if you had 100 watts, right, and you were S9 somewhere, if you all of a sudden decreased power to 5 watts, well, 5 watts, that's a 20-to-1 ratio, right? What's that in dB? Well, it's 13 dB, which is only a little over 2 S units. So if I drop my power from 100 watts to 5 watts, I just go from S9 to S7, which is still very readable. So that's sort of the reason QRP works, because this is basically a logarithmic scale. So next question, how does a signal that reads 20 dB over S9 compare to one that reads S9 on a receiver, assuming a properly calibrated S meter? Answer, it's 100 times stronger. Well, why is that? Oops, 20 dB is a ratio of 100 to 1. And these only go up to S for some reason. And who knows why? I'm sure there's some historical reason why. They only go up to S9. I don't know if you can see the 9 there, but then there's dB above S9. It's like, it seems to me they should have just said S10, S11, S12, but yeah, they don't do that for some reason. I think it's because you get the RST system, right? So the S is a signal strength, and usually you give the signal strength in, correspond to the S units. If someone's at S7 where you are, then you give them on a 7 on the S meter, you give them an S7 report. Another thing about S meters, not on the test, but S9 is supposed to equal a signal strength of 50 microvolts. And then everything else is relative to that S9, right? So S8 would be 12.5 microvolts. And then down, down, down. But again, most S meters are, a lot of S meters are not really calibrated that well. And you can figure that out. Elecraft makes a little, and it's as little and inexpensive, sort of a signal generator that only will generate a 50 microvolt signal level, like on 40 meters and 80 meters and maybe 20 meters. It's a little crystal control oscillator. And you can check your S meter with that. Any questions? All right. So let's talk about these linear amplifier questions now. This was pretty hard to. Oops, I don't even have the right. Let's see if I got it. Well, unfortunately, I don't have that diagram. Let me see if I got it. Hang on. There's some questions here about tube amplifiers and how to properly adjust them. And I thought I had a schematic here. Yeah, here you go. And I'm sorry for the sort of the lousy schematic here, but where is it? So this is a final amplifier with a tube circuit, and you have, oh heck, what am I doing here? You have some, the 7300 and all the modern radios use solid state amplifiers. There's no adjustment on the output. They're designed to output at 50 ohms no matter what. These tube amplifiers, though, and this is what we used when I was a kid even, and actually the radio they had a 6146 tube in it. There's a number of adjustments you have to make. There's the tune, the load, and usually there's here the grid current. And if you see here, you know, what do you have here? Well, you've got a pi output circuit, right? So this is, you know, it's a tuned circuit. And what you're doing is you're adjusting these values to match the output impedance to the whatever input impedance is of your antenna, and to be resonant too, right? You're matching the output impedance here to the input impedance of the antenna system. And you have to do that without drawing too much plate current from this tube. Okay, so this is the meter here, and you see there's X, Y, and Z, X, Y, and Z. Z connects here, that's the plate current. X is the grid current. And where's Y again? I forget where Y is. Oh, here's Y here. So you switch the switch and you make the adjustments. Question, what is the correct adjustment for the load or coupling control of a vacuum tube RF power amplifier? So that's the load here. Answer, maximum power output without exceeding maximum allowable plate current. So remember we talked about impedance matching. So this is matching the impedance to the impedance of the antenna system. That'll give you the maximum power, right? When the two are equal, that gives you maximum power. Question, what reading on the plate current meter of a vacuum tube RF power amplifier indicates correct adjustment of the plate tuning control? It's this thing here. Answer, a pronounced dip. So you want to adjust it so that basically the maximum current flows this way and not this way. That'll dip it. It means you have less current there and more current going out to the antenna. Now, this amplifier doesn't have this ALC control, but we'll talk about it anyway. Question, what is a reason to use automatic level control, ALC, with an RF power amplifier? Answer, to reduce distortion due to excessive drive. So here's the input power here, right? And so if you put too much power here, you're going to cause distortion because it won't be able to amplify that much. So a lot of the modern linear amplifiers have some kind of circuit here to limit the drive, and that's ALC, automatic limit control. Question, what condition can lead to permanent damage to a solid state RF power amplifier? That's, of course, not this circuit at all. Answer, excessive drive power. And again, it's the same thing. You're trying to, if you have too much input power, it'll try and amplify that. And if it's higher than what the amplifier can provide, you can actually damage a solid state power amplifier. Question, why is a time delay sometimes included in a transmitter keying circuit? And you can think of this as kind of being that circuit. Answer, to allow time for transmit-receive changeover operations to complete properly before RF power output is allowed. So if you think about a transceiver, right, you really got a transmitter and a receiver, and you got a relay somewhere switching the antenna back and forth, depending on whether you're receiving or transmitting. And you don't want to start transmitting before you've actually got a connection here. Because that means your transmitter doesn't have a load and that power's got to go somewhere, and chances are you could damage the transmitter. All right, any questions about that? So the next question talks about antenna tuners. Well, really, this is kind of the, in the old tube amplifiers, this is kind of the antenna tuner right here, because this is the circuit you find in a lot of antenna tuners. It's a pi network kind of thing. So these older transmitters could really match, a fair amount of impedances out here. So, you would always try to tune your antenna to be close to 50 ohms as possible. But if it was 100 ohms or even 150 ohms, well, you'd tune it out anyway, So, and nowadays, we just have solid state amplifiers that have a 50 ohm output, and you have to try and match that pretty closely. So in what we have today are antenna tuners, and those antenna tuners are responsible for making that impedance match. So question, what type of device is often used to match transmitter output impedance to an impedance not equal to 50 ohms? Answer, antenna tuner. Antenna coupler or antenna tuner. No, I don't know anybody that calls it a coupler anymore. All right, any questions about that? Okay. So this next set of questions has to do with, doesn't really have to do with the radio itself, but it has to do with how you operate it, how you set the transmitter frequency. So let's take the 40 meter band. Meter bands runs from 7.0 to 7.3 megahertz. You can operate phone, at least if you're a extra class. Well, we're talking about general since you're generals. You can operate phone down to 7175. So this is the general class portion of the phone band. And you want to keep your signal within that segment. You don't want to have any portion of your signal outside that segment. So in that case, and because we're operating lower sideband on 40 meters, right? You don't, and the signal can be 3 kilohertz wide. You don't want to operate any lower than 71. Don't want to set your transceiver to any lower than 7178. Because if you set it to 7178 and you're 3 kilohertz wide, it's going to take up that whole bandwidth. And you're going to still be within the general class band, subband. So question, how close to the lower edge of the phone segment should your displayed carrier frequency be when using 3 kilohertz wide lower sideband? Answer, at least 3 kilohertz above the edge of the segment. That's 7178. Question, what frequency range is occupied by a 3 kilohertz lower sideband signal when the displayed carrier frequency is set to 7178 megahertz, 7.178 megahertz? Answer, 7.175 to 7.178 megahertz. All right. So that's this. You have the same thing happen on the 40 meter or 20 meter band, but since you're operating upper sideband, you want to be at least 3 kilohertz below the edge. So you want to be, the highest you want to set your radio to is 14.347 megahertz. If you do that, then your upper sideband signal will stretch from 14.347 to 14.350. It's just the same but opposite. How close to the upper edge of the phone segment should your displayed carrier frequency be when using 3 kilohertz wide upper sideband? Answer, at least 3 kilohertz below the edge of the band. Question, what frequency range is occupied by a 3 kilohertz upper sideband signal with the displayed carrier frequency set to 14.347 megahertz? Answer, 14.347 to 14.350 megahertz. And you're still within the band and still legal. All right, any questions? All right, moving right along. Yeah, about halfway through, I think. Mobile operation. So, yeah, I mean, this is a question that a lot of people always have. Like, you know, how should you install a radio in a car? You know, that's on the amateur radio subreddit. That's like one of the most frequently asked questions, and they always ask, "Can I get by with connecting the power to a cigarette lighter port or one of these auxiliary power ports they call them?" And the answer is always no. No, you don't want to do that, especially if you want it to be any permanent kind of installation at all. And what's the reason for that? Well, you know, a 100-watt transmitter. Let's think about this. Oops. 100-watt transmitter at 12 volts, and we'll just use 12 volts for kicks, will draw 8.3 amps. Well, of course, it'll draw more than that because this radio is not 100% efficient. Even if it's 50% efficient, and yeah, that's maybe kind of stretching it, you'll draw 16.6 amps. Well, those little cigarette lighter plugs are not rated for 16.6 amps. I can tell you that. I had a friend who had kind of a disability, and he really wasn't able to do a proper installation. And he actually melted several of those cigarette lighter plugs because that's what he was operating his mobile radio with. We really should, some of us guys should have really stepped up and helped him and installed his radio properly, but he never asked and we never did. And well, that's that. But question, which of the following direct fused power connections would be the best for a 100-watt HF mobile installation? Answer: to the battery using heavy gauge wire. So you see here, he's got it directly connected to the battery, and he's got inline fuses. That's always good for protection. Question, why is it best not to draw the DC power for a 100-watt HF transceiver from a vehicle's auxiliary power socket? Answer, the socket's wiring may be inadequate for the current being drawn by the transceiver. So it's the socket too, it's not just the plug. Unfortunately, you know, mobile installations are in a really bad location to begin with. I mean, there's lots of RF noise in a car. Question, which of the following may cause receive interference in a radio installed in a vehicle? Answer, all of these choices are correct. The battery charging system, the fuel delivery system, the vehicle control computer. So, you know, you got a motor there, the fuel delivery system, the battery charging system, it's, you know, some kind of switching thing, and the vehicle control computer is, you know, digital and can also radiate RF from the cables. So all those things can cause problems. Antennas are also a big problem on mobile installations because, you know, you're never going to get rarely anyway, be able to get like even a quarter wave vertical on a car, you know. You know, if you had CB or, you know, maybe 20 meters, that's 16.6 feet, maybe you can squeeze that out, but the chances are not. So question, which of the following most limits an HF mobile installation? Answer, the antenna system. Because, you know, so say he was trying to operate 20 meters here. He's got an 8-foot whip. Well, you're going to need a pretty hefty loading coil to get that thing to load even on 20 meters, but then at 40 meters or 80 meters, yeah, that coil's going to get increasingly bigger. I knew some guys once who were operating 160 meters from their cars, and they had huge coils on their whips. You know, it was quite impressive actually. Question, what is one disadvantage of using a shortened mobile antenna as opposed to a full-size antenna? Answer, operating bandwidth may be very limited. So that's what happens, you know, with these, even though you can get it to resonate on a certain frequency, the actual bandwidth may be pretty narrow. So there's a type of antenna, and this is sort of looks like one, called the screwdriver antenna. And I think we talked about this in the antenna section, but what they do is they drive a slug up and down the center of this coil, which changes the inductance, which then changes the tuning of the antenna. So this tuner drives that coil up and down, and it senses the SWR and makes the thing work properly. The bandwidth is still limited, so if the operator changes frequency enough, then the tuner has to retune the antenna. Another way sometimes you see on cars is they'll use a capacitance hat. So up at the top of the antenna, they'll have a capacitance hat. And what does that do? That's the same thing as putting a loading coil at the bottom. It increases the electrical length of the antenna. So question, what is the purpose of a capacitance hat on a mobile antenna? Answer, to electrically lengthen a physically short antenna. The reason I got around that, the next question has to do with the tip of the antenna here. Question, what is the purpose of a corona ball on an HF mobile antenna? Answer, to reduce RF voltage discharge from the tip of the antenna while transmitting. So you see, even here they got one, but sometimes they're even bigger. And that distribute, so you have a pretty high voltage at the tip of a short antenna, and that just sort of disperses the charge, which prevents this thing from arcing. All right, any questions about mobile installations? All right, we have a guy here who works at Chrysler. Well, it used to be Chrysler, now it's FCA, it stands for Fiat Chrysler. Anyway, he drives a hellaciously long way from Ann Arbor to Auburn Hills in Michigan, and that's over an hour drive each way. And he's installed HF equipment in his truck. He's got a big pickup truck, and he's actually, he's an engineer, he's an electrical engineer with the company, and he's fought battles with their EMC guys because one truck he had just was really terrible as far as radiated noise is concerned, and I think he finally got it fixed, but it was quite a struggle. All right, let's talk about solar power. This is actually my pride and joy. This is the solar installation I had for field day. I got extra points for it at all too. I had this big long solar panel here that our club bought a bunch of solar panels from a company that was actually making them here in Michigan, oddly enough, and they were going out of business. So we bought a whole bunch of these solar panels, and I connected it up to this solar controller here in my battery, and that's all I used on field day. Over 12 hours of operation, and it worked like a charm. I was really, really happy with it. So a couple of questions here about solar power. Question, what is the name of the process by which sunlight is changed into electricity? Answer, photovoltaic conversion. Sometimes they call these PV panels, photovoltaic panels. Question, what is the approximate open circuit voltage from a fully illuminated silicon photovoltaic cell? 0.5 volts DC. And and here these things are all connected in series and parallel. And you at the controller here, you get anywhere from like 12 to 24 volts, maybe not quite 24 volts, but that all depends on the illumination here. And it's the job of the solar panel controller, the solar controller, to charge the battery and or power the radio. Question, what is the reason that a series diode is connected between a solar panel and a storage battery that is being charged by the panel? Answer, the diode prevents self-discharge of the battery through the panel during times of low or no illumination. So, So what happens here is, so say this is the solar panel and this is the battery. If you put the diode in this way, when there's low illumination, this might go more negative than the battery, right? And if you got the diode inserted in this way, you're not going to get current flowing back into the solar panel. That's the whole idea of this question. I don't know if this solar panel had a built-in diode or not, or maybe that was taken care of by the solar controller in this case, but that wasn't a problem with my installation. And finally, a question about wind power, and this is sort of a duh question. Which of the following is a disadvantage of using wind as the primary source of power for an emergency station? Answer: a large energy storage system is needed to supply power when the wind is not blowing. All right, any questions about that? All right. Don't say I didn't give you a shot. Oh, there it is. All right, so let's talk about test equipment. Yeah, there's a lot of questions about multimeters in the tech test. There are only a few here, but the first question has to do with analog versus digital multimeters. So this is obviously the digital multimeter. This is the analog multimeter. It's the venerable Simpson 260. You'll hear it, some of the older guys wax poetic about this thing. Apparently it was very common in the military. They had a militarized version, and that's what people use with these Simpsons. But digital is the way to go. Okay, digital really is the way to go. This is a fluke. This one is actually a little bit expensive, but you know, you can get a good digital meter for, you know, $30 to $40. And this thing will cost you several $100, you know, if you can even, I think you can still buy them. I think they still make them. But this one will actually make better measurements than the Simpson. Question: what is an advantage of a digital voltmeter as compared to an analog voltmeter? Answer: better precision for most uses. And you know, they're great. Question: why? And one of the reasons is this has a higher input impedance because they're using field effect transistors in here, and they have a very high input impedance. Question: why is high input impedance desirable for a voltmeter? Answer: it decreases the loading on circuits being measured. So that's another reason it provides better measurements. Having said that, an analog meter may be useful for some applications. Question: what is an instance in which the use of an instrument with an analog readout may be preferred over an instrument with digital readout? Answer: when adjusting tuned circuits. And why is that? Because, you know, you see the needle move back and forth here, and as you're adjusting, you can tell if it's which way it's moving instead of trying to figure it out from the numbers, and you can tell how fast it's moving. So it's moving slowly, but in the right direction, you crank it up a little faster. If not, you make it a little slower or switch, you know, adjust the other way. So sometimes it's useful to use a meter like this. And, you know, in the case of that final amplifier, that was an analog meter there because you're, you know, making a sort of a continuously variable adjustment there, if you will. Any questions about multimeters? This is actually kind of one of my areas of expertise. I used to work for a magazine called Test and Measurement World, and I wrote about test equipment. I did that for 6 years. So if you ever want to know about multimeters or oscilloscopes here, I'm your man. So oscilloscopes used to be really expensive, and the reason for that is that, you know, they were, you know, they were analog monsters, they had used large vacuum tubes, and those vacuum tubes required high voltage supplies. Well, nowadays, you don't need any of that. All these new oscilloscopes are digital oscilloscopes, meaning they use all semiconductor circuits and sort of like computer displays, LED displays, LCD displays. So you see, like here, you know, it's this distance here is like, you know, 4 or 5 inches. The other scopes, you know, they'd be, you know, 2 feet long. So these are, you know, they're lighter. They're actually in a way sometimes more accurate, and they give you because they've got digital signal processing built into them too. They can provide a lot of different types of measurements. I don't think you can see it too much here, but like, you know, it can tell you like peak voltages and frequencies. What's the frequency of this signal and all that kind of stuff. You know, what the pulse width is here. It'll have those measurements right on the screen. So oscilloscopes are really great. And you could buy this one. Let's see, this one, I can't really see it, but I think it may be 100 megahertz scope. You can get that for probably about $300. I mean, that's really cheap. These older ones with the big tubes and all, they were like $1,500 and up. I had a 60 megahertz Tektronix scope for a long time that I paid like $1,500, well, 12 or 1,500, I forget, 1,200 or 1,500, back like 20 years ago, you know. So nowadays these are cheap. So question, what type of let's start with this second question first here. Which of the following is an advantage of an oscilloscope versus a digital voltmeter? Answer, complex waveforms can be measured. So you see, we can see the actual waveform. If you had that meter, it might give you a number. It might tell you like the RMS value of this waveform, but it couldn't tell you that it's actually a square wave, or that it's, you know, sort of a weird periodic waveform. It can't show you the actual waveform itself. Question, what item of test equipment contains horizontal and vertical channel amplifiers? Answer, an oscilloscope. So, you know, you've got 2 dimensions here. The horizontal is time, and then the vertical is amplitude. And so you can change the settings here to make the waveforms bigger or wider. And those are, you do that by adjusting the horizontal and vertical amplifiers. And actually, they're not even amplifiers anymore. In these digital scopes, it's just a digital setting. These control, you know, in the analog scopes, they used to be actual potentiometers, and now they're just encoders that tell the computer how to display the waveform on the screen. Question, which of the following is the best instrument to use when checking the keying waveform of a CW transmitter? Answer, an oscilloscope. And that's this display right here. This is a screenshot from an oscilloscope, and it shows how the input keying is and the resulting RF output. This came out of a QST review of a transmitter. They do this for the product reviews. Question, what signal source is connected to the vertical input of an oscilloscope when checking the RF envelope pattern of a transmitted signal? Answer, the attenuated RF output of the transmitter. So you can, you know, connect a transmitter to your oscilloscope, assuming you go through an attenuator of some kind. You can connect that right up there and then see the transmitted signal. assuming you have enough bandwidth, right? So if this was a 14 megahertz signal, 20 meter signal, yeah, you got enough bandwidth. 2 meters though, 144 megahertz, yeah, probably not. Any questions about that? All right. So now we're going to talk about this assortment of meters here in different fashions. These are all things you might use to work on your antenna system. One of the big things is an antenna analyzer. I love antenna analyzers. When I was a kid, we didn't have antenna analyzers, and I was never very good with antennas. I'm still not great with antennas, but I'm better. And why is that? Because I have an antenna analyzer. I can make measurements on an antenna, and it tells me stuff about the way the antennas work. Some hams are just like totally intuitive when it comes to antennas. This is almost true. They come over to your house and they'll look at your antenna and say, "Oh yeah, I know why this isn't working now just by looking at it." It's like that was over my head. But with an antenna analyzer, I can make some measurements and figure things out. And the antenna analyzers can do a lot of things. They'll make SWR measurements. You can measure. You can do measurements to tell you if your coax is good or not. I'll give you an example of that. So one time I was having a problem with my antenna, and I didn't know if the coax was any good or not. So I put an antenna analyzer here. I put a dummy load here and measured the SWR. Well, this is 50 ohm coax. Well, in my case, it was 75 ohm coax. With a 50 ohm dummy load, I should read 1.5 to 1 on my antenna analyzer. But since the coax was acting funny, I got just weird readings. But at least I was able to do this and then eliminate the antenna itself as the source of my problem. So the solution here was to replace the coax, which I did, and everything worked fine again. So question, which of the following must be connected to an antenna analyzer when it is being used for SWR measurements? Answer, antenna and feed line. This is kind of a stupid question because that's what you're making the measurement on in the first place, is the antenna and feed line when you're measuring SWR. Question, what is a use for an antenna analyzer other than measuring the SWR of an antenna system? Answer, determining the impedance of coaxial cable. So in that, I shouldn't have erased that, but in that case, if I have a known load, 50 ohms, then the cable, if the cable's not 50 ohms, it'll read something other than 1 to 1, and then using that SWR, that ratio, I can then make some conclusions about the impedance of that cable. Question, what problem can occur when making measurements on an antenna system with an antenna analyzer? Answer, strong signals from nearby transmitters can affect the accuracy of measurements. And again, this happened to me too. This is for the Michigan QSO Party contest. Our club was going to set up a multi-station operation. So we go over to this guy's house and we start setting up some antennas. And I get out my antenna analyzer and I'm measuring the SWR of my antenna to see if it's tuned properly. And all of a sudden I start getting funny readings, like really high SWR readings, and then they'd go away. And I'm thinking, oh, what the heck's going on? Well, some other guy was testing out this transmitter, and I was actually picking up that signal. So because what happens when you're using an antenna analyzer, you're injecting a small signal into the antenna, and you're looking for the reflection from the antenna, and so you're calculating the ratio based on those measurements. Well, if somebody else is transmitting, a nearby transmitter, that energy is going to look to the antenna analyzer like reflected power, and that just throws off the measurements. So that was kind of amusing. Well, it took us about 15 or 20 minutes to actually figure that out. I hate to admit it took us that long, but it did. But yeah, antenna analyzers are great. They really are great. Any questions about that? All right, we'll move on to the watt meter. So this is This is the venerable Bird 43 watt meter, and you see there's a arrow. So the way these meters work is you have these slugs, and they call slugs, and they plug into the watt meter in that spot. And you see that they all have a frequency range. So this is 100 to 250 megahertz. So this is probably being used to calibrate or measure or adjust like a repeater or a pager system or something that operates in that frequency range. You see it's got an arrow here, right? So when the arrow is pointing in this direction, you're measuring the power that's going in that direction. Usually this is forward power. Usually you connect the transmitter here and the antenna here. So that's forward power. When you can turn the slug so that then the arrow is pointing in that direction, and you're measuring reverse power in that direction. And what these guys do when they set up repeaters is they just maximize for forward power. So they tune they have these cavities. They tune the cavities for maximum forward power, and then just check the reverse power just for kicks. But usually, if they adjust the cavities for maximum forward power, they get little or no reverse power, and that works out. They don't really care what the SWR is. However, if you really wanted to know what the SWR is, you could calculate it from those two readings. And in the study guide, I give you that equation. I'm not going to run through it here, but you can do it. And that's the question. Which of the following can be determined with a directional watt meter? Answer: standing wave ratio. Moving on to our third meter here. This is one of those cheap SWR power / field strength meters. And the way you get field strength is usually put a little whip antenna in there on it. And then you set it for the power reading and you can measure the power. Question: which of the following instruments may be used to monitor relative RF output when making antenna and transmitter adjustments? Answer: a field strength meter. And really especially these cheap ones, they're only good for like indicating whether or not you're outputting any power at all. I mean, they're not really that great. Question: which of the following can be determined with a field strength meter? Answer: the radiation pattern of an antenna. So theoretically, if you had an antenna here, you could take a measure in here, all the way around the antenna, and then come up with what the antenna pattern is, right? But I've never known any ham to actually do this, so take that with a grain of salt. But the answer here is the radiation pattern of an antenna. Any questions about that? Okay, let's talk about the two-tone test. The two-tone test is a thing you might want to do on your transmitter. And what it does is it measures the linearity of the transmitter. So what you do here is oops. Oh, I don't want that. You input two tones. Not two non-harmonically related tones. Sometimes they use 700 hertz and 1900 hertz. You input that into the transmitter. If the transmitter is linear, you'll get 700 and 1900 hertz on the output. If it's not linear, they'll mix and you'll get some other frequencies. You can use a spectrum analyzer to analyze the output, or you can use an oscilloscope. If you feed the attenuated output of a transmitter into the oscilloscope, you'll get the transmitter is linear, you'll get this nice pattern here with a very small crossover here. I suggest that you watch this YouTube video. This is done by a guy whose call sign is W2AEW, and he's actually a Tektronix, which is a big maker of oscilloscopes and other equipment. He's one of their applications engineers. He's a very knowledgeable guy, and he has a ton of good YouTube videos on different ham radio topics. This really is a great video. It's only 4 minutes long. It's like 4.5 minutes long, and he walks you through this two-tone test. So, question: what type of transmitter performance does a two-tone test analyze? Answer: linearity. Question: what signals are used to conduct a two-tone test? Answer: two non-harmonically related audio signals, meaning that they're not dividable or by a whole number. So, you know, if this was, you wouldn't want to use 2100 hertz, in other words. Any questions about that? The two-tone test. I've never actually done one myself because I don't operate that much phone, but it actually, after watching this video, it actually looks like a pretty easy test to do. And again, Elecraft makes this this little board. It's, I don't know, it's 30 or 40 bucks that generates two tones and makes it easy to do. In this video, he uses a fancy signal generator because he's got access to a fancy signal generator. But you can do this with this little Elecraft gizmo too. All right, let's talk about radio frequency interference. So your station obviously can cause radio frequency interference. My own station every once in a while seems to cause radio frequency interference. And the odd thing is it doesn't do it all the time. So I have a devil of a time trying to figure out where it's, and it doesn't do it very often. So I have a devil of a time trying to figure out what's wrong. But a lot of things can happen, and because there's a lot of things going on, right? And this is actually the best sort of diagram I could come up with to show things that go on. And you can think of these things in a ham radio context as the source sort of being the antenna, right? The victim, well, it could be your own radio, your transceiver, or maybe an FM receiver in your house. Or if you're still doing TV over there, maybe a TV. And these are different ways that the signal from your antenna can couple into the victim, as they say here. You know, it could be inductive, it could be radiative, it could be capacitive, it could be conductive. So all these things can happen. Question: what sound is heard from an audio device or telephone if there is interference from a nearby single sideband phone transmitter? Answer: distorted speech. So, you know, you can hear that on these devices. What is the effect of an audio? What is the effect on an audio device when there's interference from a nearby CW transmitter? Answer: on and off humming or clicking. So, I mean, you're not, obviously a CW, you're not going to hear speech, but you might hear this clicking. So how do you fix this stuff? Well, question: which of the following might be useful in reducing RF interference to audio frequency devices? Answer: bypass capacitor. And let me show you an example of that. So at our station at the Hands-On Museum, we had one woman who was complaining that she could hear our transmissions in her PC speakers. And hers was the only one that did that. I mean, they had a bunch of PCs in this office. So we said, well, why don't we just change your speakers? Oh, she says, no, we don't want to. I don't want to do that because she was somehow, some reason, attached to those speakers. I guess they sounded pretty good, except when we were transmitting. So we never actually did this, but there's one thing we could have done. So you got the speaker here, right? And you got the lines coming into it. Well, you could put a bypass capacitor right across the speaker inputs. What does that do? Well, if you recall, as the frequency goes up, capacitive reactance goes down. So at audio frequencies, this is going to act like a short circuit, and she'll still hear the audio, but at RF, it'll act like a short circuit, and the RF won't get into the speaker. There's a company called West Mountain Radio. I think it's West Mountain Radio. West Mountain Radio that makes what they call is a hardened speaker system for PCs that you're supposed to be able to use in your shack and not have any RF interference. I contacted them. I said, well, what's the secret there? Oh, we can't tell you. It's a secret. So they wouldn't actually tell me what was in their speakers, which is kind of stupid. But chances are all they had was a bypass capacitor in there. So because they wouldn't tell me, I'm never buying a West Mountain Radio product ever again. I thought that was pretty crummy that they wouldn't tell me. Question, which of the following will reduce RF interference caused by common mode current on an audio cable? Answer, placing a ferrite choke around the cable. So that's sort of another thing you can do, right? You can put that ferrite choke on there. And what does that do? That makes sort of is like putting an inductor in series with the speaker. And remember, X of L goes up as the frequency increases. So that's like putting a big resistor at RF frequencies in the line. Again, reducing the amount of RF that can actually get into the speaker and cause interference. And you might do both just for kicks, just to, belt and suspenders kind of thing, just to see what works best. And what do I always say? Have a handful of RF chokes in your shack because you never know when you'll need them. Any questions about that? Get those chokes. Here's the last topic: ground loops. I couldn't find a diagram of a ground loop in a amateur radio shack, so I kind of cadged this one. Ground loops are a problem, right? And so you want to eliminate ground loops if you can at all costs. Because what happens here? Well, you get current flowing, and that raises the ground level, and so the ground isn't the same at all, and that's and if you get some radiation in there, then some noise pickup, then that just makes the ground go up and down, which makes the in this case the stereo hum, or in the case of audio cable, it makes distorted audio in your shack. Question, how can a ground loop be avoided? Answer, connect all ground conductors to a single point. So one thing this installation could have done is, instead of connecting these to two separate power sockets, connect them to the same power socket. Yeah, you still got a ground loop here, but it's less of a ground loop, meaning that you probably get less noise pickup. So that's the thing to do. Connect all grounds to a single point. And I actually have an image of that. Let me show it. So this is what they're doing. They're connecting all the, if you have multiple pieces of equipment in your shack, which a lot of times you do, you connect them all to a single point. and then you run that to the ground. Question, what could be a symptom of a ground loop somewhere in your station? Answer, you receive reports of hum on your station's transmitted signal. And again, it's, you know, it's picking up that 60 hertz hum. So let's talk about this grounding for a second. So what you want to do is you want to use a good ground strap. That's what this is, a ground strap, right? Flat strap. Why do you want to use this kind of strap? Well, if you recall, there's a thing called the skin effect. So RF flow tends to flow on the surface of a conductor. Well, if you have many small conductors all connected together, it's like you have many different connectors connected in parallel. And so the total resistance will be a lot less than at RF than just like a big single conductor. No, that's not a good drive. So that's why we use flat straps. So if you put flat straps for these connecting to a single common point, and then just run one length to the ground rod, that's good. That's a good practice. However, you want to be careful here, because what do you have here? Well, you can think of it as almost as part of the antenna system. And if it's like a resonant length, then you really don't have a ground connection here. You've got part of your antenna, and you can have high voltages on there at certain frequencies. So question, what effect can be caused by a resonant ground connection? Answer, high RF voltages on the enclosures of station equipment. And why is that? Because this is all connected to ground, which is connected to the metal of the chassis. So you could have a high RF voltage on the chassis. Question, what might be the problem if you receive an RF burn when touching your equipment while transmitting on an HF band, assuming the equipment is connected to a ground rod? Answer, the ground wire has high impedance on that frequency. So again, that's, could be a reason not to use a long ground wire, or there's certainly one that's not a particular length. Question, why must the metal enclosure of every item of station equipment be grounded? It ensures that hazardous voltages cannot appear on the chassis. That's like a safety thing. What techniques helps to minimize RF hotspots in an amateur station? Answer, bonding all equipment enclosures together. And that's what they're doing here, bonding them all together. MFJ actually makes, and these are the only ones that make this. They make a thing called an artificial ground. And you stick it in here, and what's it doing? Well, it's making this length non-resonant. So it's sort of like the reverse of an antenna tuner. It's kind of an odd device. Like I said, MFJ is the only one that makes it, and I suppose it might be useful if you don't have, you do have to run a long wire to the ground. But I don't know. I've never heard of anybody that's actually using it. Any questions about that?
I have a question.
Yeah.
About grounding. Before, when we talked about the mobile thingy in the car,
Yeah.
there was no mention about grounding. Why? Is that because we're on rubber deck or what?
Well, so good. That's a good question. And you still want to have grounding. Let me go back to that. Oh, shoot. Oh, I hate that. I don't know how to get that. So you see what they do here is they connect directly to the battery, even the ground, because, you know, theoretically you could, oh heck. Theoretically you could, you know, ground like to the body of the car somewhere, right? And somehow, some way it gets back there, but then you have a long ground lead, and you can have voltage, sizable voltage drop across there. So you don't want to do that. You want to connect directly to the battery, as
Okay.
directly to the battery as you can. And,
All right.
and then as far as, you know, then the chassis will still provide the ground plane for these antennas, but that's the RF ground, not the DC ground, right? And if the antennas are, the ground is, you know, bonded there, then, you know, that's different than the DC ground. That's the function is different. Okay.
Well, I guess I will have to think about it, but I guess it's okay.
Yeah, I know. This is great. You know, grounding is one of those things that in ham radio, especially, well, I suppose in anything that needs grounding, that there's continual debate about. You know, like, you know, for example, I don't do anything special at my station, and things generally work okay, except now I do have a problem with this flex radio on band, like the 15-meter band. When I tune up on it, I get all kinds of funny things happen. And that's because I'm getting RF feedback into one or more of the cables and or the Ethernet switch, which I need because it's the Ethernet switch that connects the digital signals from the radio into the computer and vice versa. And you need both are the radio in effect. So I need to figure out something better at my station. And probably what I need to do is to do exactly what, let me get rid of this again. Oh, where is it? What I need to do is come up with a single point ground and somehow probably mount that Ethernet switch to it, just so that everything has a common ground. But I haven't gotten around to that yet. I just don't operate at 15 meters, which is stupid, I know, but I don't know. That's the way I do it. But what my point is that it's an important thing to do, especially when you have problems. And you know, if this was a professional installation, if I was doing a professional radio installation, I would probably do more. I would make sure that everything was grounded properly. You know, in an amateur station, you're changing things frequently and such as that. So yeah, I don't know. It's less of an issue, I think, but still, it's something you want to pay attention to, because when problems happen, they take you off the air. So that's something to think about.
All right, thank you.
Yeah. And finally, this last question: which of the following could be cause of interference covering a wide range of frequencies? Answer: arcing at a poor electrical connection. And why is that? Well, it's like a little lightning bolt there, right? And it just spews out radiation on all different frequencies. So if you got that, you know, that's what happens on power poles, right? Power poles sometimes develop arcing connections, and they create RF interference to your station. So that's not like even something that you can control at your house. You know, if you have arcing, just put it this way: if you have arcing at your house at one of your outlets, that's really bad. You should take care of that immediately. If the power company has some arcing, you know, call them up and get them out to look at the lines, because that's bad for them too. Because eventually those things will fail, and then lots of people will be without power. All right, any questions? All right, that's it then.
Thanks, Dan.
My pleasure as always. Just one more class left, remember? We're talking about the
Yep.
rules next week. That's really boring. If you want to skip that, feel free to skip it. But
Thanks a lot, Dan.
yeah,
Thank you, Dan.
Have no good
Thank
night.
you. Good night, everybody.
Thank you.
Thank you. Good night.
Thanks a lot.